Welcome back. So we've been recently talking about rotational motion, so we're going to continue doing that today. We'll get into something important that is equivalent to mass in rotation called the moment of inertia. That's a big concept to think about when we talk about rotation, so we'll get into that. Showing the animation right here, I have the Earth rotating around its axis. Thinking about rotational motion, I said, think about when you are in your everyday life, what are the objects that you might see in a rotational state, right? So when you're thinking about concepts in physics that you're learning, try to apply it to your everyday life. I'm sure you notice now, hopefully more, that the things that are rotating, and then you can think about how fast, or is it becoming faster? What's causing that rotation, right? So these sorts of questions you're asking. So here's the Earth, example of rotational motion. Today we want to talk about some key words that we've seen at the very beginning of the class: position, velocity, acceleration. We're going to give them angular equivalents, right? So angular position, angular velocity, angular acceleration. And then we'll talk about their kind of counterparts to translational, the equations of kinematics, translational variables like velocity, right? So how does it relate to angular velocity? We'll talk about that. Good thing is everything basically you've learned from kinematics, you can transfer and swap out the terms, and they function essentially the same way. And same thing for Newton's second law. So there's a Newton's second law for rotation, which you can use to solve problems. And along the way, we'll talk about the moment of inertia, which is going to be kind of what is like mass in rotation, right? So you need something like mass when you're talking about rotation, and that's the moment of inertia. Okay, going to our notes, let's set up some of these variables. You're thinking about rotational motion. So I'm going to put down an XY coordinate system here, kind of the regular coordinate system. And let's think about some point that is going around a circle, okay? So this point could go around the circle. So if you want to think of an example, you can think of a record, for instance. If you have records, listen to music. Imagine thinking about a little point on the record, and as the record plays, that point goes around, right? So that point can go from point A, and after some time, that point will be over here, right? And it'll be at point B. Okay. So along the way, it has a certain position vector, right? So you can, from your origin, you can point to where it is, locate where it is, and call that R, right, your position vector. So from that center, you locate where your point is, and you can do that. And when it rotates over, you can still do that, right? You can still point to where it is, and that's its position, the vector, and it's changing, right? So as the point goes around the circle, your position vector will also track it, right, and change as well. So that's position. The vector is a translational idea, right? You can think about a car going in a straight line, for instance, or something like that, where you have a position. But when you're talking about something rotating, we really should be talking about an angular position. Right? So it's more convenient to think about it this way as an angular position, because this is not that convenient to use position this way, right? We can still use the ideas from before, but when you're talking about rotation, better to use actual proper position that relates to rotation. So how we're going to do that is that we're going to take this angle, theta, to be our angular position, okay? When we say angular position, that's what we mean. Much more convenient to track the angle when you're talking about something going around in a circle than it is to track kind of this location versus this location, right? Particularly if it's a circle, the radius, the magnitude will be the same, and it's an issue of tracking the direction of the vector, which is not that convenient. But the angle is pretty nice, right? So if you say I'm going to measure from the x-axis, I can measure in a positive direction through theta, and we can all agree what that means, right? So we measure this way, for instance, and we say that's our theta, our angular position. So the angular position is related to your radius here, and this length here, this arc length, we'll call that S, right? So this distance here along the arc, right? That distance S. So angular position is that arc length divided by the radius, okay? And you'll list angular position in radians, okay? Standard units will be radians, more on radians in a second. But that's how we're going to define angular position. Now, you might look at this and say, hey, okay, that seems kind of, where did that come from, right? Why is it S divided by R, not R divided by S, right? So why does it follow this way? And you can think back to kind of your math class where you looked at what is S in terms of going from point A all the way around and coming back to point A. Right? From your math class, you probably remember that is the circumference of a circle. And so going from point A all the way around the circle and coming back to A, that's 2 pi r, right? Circumference of a circle. If you write that 2 pi r, that's your S. And then if you divide by r, you're going to get 2 pi, right? So it's saying that the angular position, if you start at A and go all the way around the circle and come back, the angular position is 2 pi radians, right? So you know that the angle of a complete circle, right, going around completely, is 360 degrees or 2 pi radians, right? So if you ever forget this relationship, just come back to your circumference, right, and what is the angle going from A to all the way around A, right? You can actually get this back if you ever forget how this goes, right? Because it's kind of related as expected. Okay, so one note about radians. Radians are not units like meters, right? Like kilograms. It is more of a label. Yes, we kind of treat it as units, right? We list it like this, like we would list meters or kilograms, but they're not as serious of a unit as meters or kilograms or seconds are, okay? And that hint comes from right here, right? Because if you think about the length, right? Standard units for length is meters. Standard units for radius, right, is also meters, right? So if you have meters divided by meters, you have no units here, right? So these cancel, and then on the left-hand side, you're left with also unitless entity, right? So your angle is unitless technically, but we don't want to confuse ourselves when we just say 2 pi. Do we mean 2 pi or do we mean the angle? So therefore, we have this label when we have an angle, right? So technically, this angle doesn't have any proper units, right? Not like meters. So radians, just be careful with radians. They are kind of the standard thing to use. Degrees are less standard if you think about what's the standard for angles, but not very strict units in the kind of the meters, kilogram sense. Okay, so this is a good start, but we need to make this a little bit more complicated to talk about other things in rotation, right? So it's not really that critical to go to this next step for angular position, but it's really important for angular velocity, and when we get to angular momentum, things like that, what we're going to do next is important. So pay attention to this, and we're going to make it a little bit more complicated because we need it to be a little bit more precise. So what we're going to do is draw this exact same picture, but in a three-dimensional sense, right? So what I'm going to do is rotate my coordinate system where x is over here, y is over here, and this is going to be positive z, okay? And I'm going to redraw the setup as is, but notice that this going around the circle, let's say your record player, was in the XY plane. So I'm going to draw that in the XY plane once more. Okay, so we started at the x-axis. We're going around a circle. And coming back, okay? So a little hard to draw this, but you kind of get the idea. So we have this, right, that a circle is only in the xy plane, and we want to redraw that in the xy plane, nothing in the z, right? So it's still flat. It doesn't have a z component, okay? And what we're going to do is still think about our point A, okay? And we have a position vector, right, our radius, r, and a little bit along the arc length, right? Instead of going from A to B, maybe you want to go a little bit further along, but not too much, a little step in that direction. I can depict something like this, right? So the little step is a vector itself. Okay, I'm going to still call it S. Okay, and I'm just trying to show a little step perpendicular, right, to the circle, tangent to the circle. And I'm taking these steps. Imagine if you took a whole bunch of these steps, you'll end up back where you started. You go all the way around the circle, okay? So this angle, right, this angular position, we're going to make it into a vector. Okay, so what we're going to do is say that this angle is going to be represented by this vector that points in this particular direction. Okay, so this is theta, the vector. Okay, remember, this is still angular position, right? It's the arc length over the radius, right? It's some angle, essentially. But we're giving that angle a direction. Now, this seems a little kind of contrived, right? Maybe it's uncomfortable to you because you're saying, wait, the angle is an angle, right? Why does the angle have a direction? It's just because we want we want an ability to say if we're going from point A to point B, if we're going that direction, notice we're already drawing some sort of arrow to indicate we're going from A to B, right? Going from B to A is different. The magnitude of the angular position or angle will be the same, but going from B to A is a different direction, right? So we want to be able to kind of account for this, right? It's not just the angle and done. There's a certain direction to the travel, right? So are you going clockwise or counterclockwise, right? The words we use, clockwise, counterclockwise, we're trying to give a direction, right? So what we're trying to do here is instead of saying counterclockwise and clockwise, we're giving it more of a precise direction. We're saying, oh, okay, it's a vector. It points in this direction, okay? So how you find this out, right, how they're all related is through the right-hand rule. And so this is why it's important to really understand the right-hand rule. So S, the vector, is equal to theta, the vector, cross product with R. Okay, so that's why all these are pointing in the way they are pointing, right? So they're related through the cross product, and it's important to do theta cross R. You can't just do some combination of this. It's theta cross R is the direction of S. Okay, so take a moment, good chance to practice your right-hand rule. Ask us questions on a discussion. There's a thread going on for the class today, right? So general questions. Anything about the right-hand rule. So do the right-hand rule either way, like the fixed finger method, curling method, either one you want to use. But make sure you're doing the cross product, theta cross R, and you're getting the direction of S as shown in this diagram, right? And before we move on, we want to make sure we're all on the same page here. How are we doing? Questions so far?
No question.
No, not yet. Okay. Make sure you're trying the right hand roll, right? So do you agree that the way I've drawn, don't just go with my diagram, what I'm just saying, right? So make sure you're checking this for yourself. See if that makes sense to you. How's the direction for you? So when you do the right hand roll, do you get S to be the way it's shown here?
Yes.
Yeah, you get the S to be this way, right? Okay, let's try that, right? So let's do it both ways so that you have practice. Let me zoom out here so that hopefully you see my hand, right? So I'm zooming out here. Theta cross R, fixed finger way. Index finger's got to be theta, right? Index finger is always the first vector. Whatever is shown up, something cross something, that's the first vector. That's your index finger. Goes along the direction of theta. Your middle finger goes along the direction of R, right? So theta cross R, notice where my thumb is pointing, right? It is hard to show the orientation like this because this is 2D, my hand is 3D, right? So it's harder to do this, but hopefully you're seeing, right? So theta is going kind of that way, R is pointing in that direction, and my thumb kind of points in the direction of S, right? And you can do it with the curling method too, 4 fingers along theta, curl towards R, right? So you kind of have to rotate your hand a little bit because it's not just this, right? Because the Z-axis and the X-axis are not on the plane of the page, right? Because Z is like this and X is kind of at an angle. So Z, right, the theta cross R, thumb is pointing kind of in that direction, right? So on Ed Discussion, there's a post at the very top, right, additional resources. I posted a video of doing the right-hand rule using Desmos, right? So Desmos it's got a 3D graphing calculator there. So you can put the vectors and kind of rotate the coordinate system. That way you can visualize it in 3D. So try that out. That'll hopefully help you a little bit with the right-hand rule. Part of the issue is it's three-dimensional, so it's hard to draw on paper. And then when you do the right-hand rule, it's three-dimensional, right? So that's part of maybe the confusion. So questions about that? Do you all see that, or everybody's clear on the right-hand rule so we can go to the next thing?
Why do they need to give theta direction and why is it in the Z direction?
Sorry, say that one. Which one?
Why do they need to give theta a direction and why is it in the Z direction?
Yeah. So the theta has to have a direction because it matters if your record player is going counterclockwise or clockwise, right? If something's spinning, like the Earth, right? You have a water bottle, right? If I'm water bottle spinning, right? Something like that. Whatever is turning, it's not sufficient to say it rotated by 30 degrees, right? Did it rotate counterclockwise or clockwise, right? So here in this case, when I say A goes to B, it has a certain direction, and we've already drawn an arrow like this, like with a curve. That's not a vector, I'm just drawing a direction, right? So I already need some sense of direction for the angle. And instead of calling it counterclockwise, clockwise, what we're doing is saying it points in a certain direction, right? And it's not very intuitive why it's this direction. It's not that important, really, that this vector points in this particular direction. It's just that this is one orientation and the opposite is the other option you have, right? So imagine that you, instead of taking steps along this way, you took the steps in the other direction, right? You went that way, right? So then what would happen to theta is theta would be pointing downward. And if you do theta cross R, right, then that would give you S pointing that way, right? So it's consistent. So the direction of theta is really trying to tell you which way are you traveling, right? Are you going around the circle clockwise or counterclockwise, right? Does that make sense? And that's why we have to give it a direction. It's not, well, I mean, one could say you can say positive or negative, right? That's perhaps an option. This is a little bit more precise when you're doing it this way than to say positive, negative. Does that make sense? Yeah. So you need to kind of, it seems contrived, like I said, it's like, okay, why does the angle have a direction, right? when you take something and toss it somewhere, right? You have a certain thing, a velocity. When the velocity vector points like that, it's kind of obvious, right? That it's moving that way, then the velocity vector is that way. When something's rotating, its angular position, right, is pointing in an odd direction, and that's because we need to say, is it clockwise or counterclockwise? And this is kind of a more precise way of saying clockwise or counterclockwise, right? Other questions about that? I think there was a second part to that, was there? Kyla?
Why is it in the z direction?
Yeah, right. So z direction. That part doesn't strictly matter. It's that we are going to use the right-hand rule to kind of make sure that all these directions are consistent with each other. And so that's part of the reason why it's up, right, then down. You could have picked a left-handed coordinate system and done something different, but we would like to be very consistent, right? We're using the right-hand rule for many different purposes, and it's a way to be consistent with the directions, right? So theta. If you're not clear where theta is, guess a direction, do theta cross r, and see if your steps are in the right direction, right? Because you might know which way you're going already, right? You're taking steps along this direction, and you're trying to determine what the direction of theta is. Take a guess, right? Take a guess of what it is, do theta cross r, and see if your s is consistent with that, right? Okay, so we have angular position, right? Just like before when we started the class, we talked about position. And now what we're going to do is talk about angular velocity, right? Natural next step to this. And yeah, please keep asking questions about this as we go. We're happy to help. Okay, angular velocity. Let's again have a coordinate system, x, y, z. And let's have a disk that's spinning. It could be your record, for instance. Any object really that's spinning. So we'll have this disk. And let's say it's spinning around kind of like this, right? So from the top-down view, counterclockwise, right? If you're looking from the top here, it will look like this disk is rotating counterclockwise, right? Now, let's think about what is angular velocity, right? And we know from before, it's got to somehow relate to a derivative with respect to time. So angular velocity, we use the Greek symbol omega, is the derivative of theta with respect to time. Okay? So we're talking about how much of this angle is changing over time, right? So that should kind of make sense, right? In terms of what an angular velocity is. Now, we need a direction for this, right? Just like with theta. And so the way we're going to do that is kind of come to the very edge of the disk, identify a point, and you'll notice that that point itself, at a moment in time, will go tangent to the disk, right? It'll have a velocity, like regular velocity, right? Like linear velocity. That little point right there, if you watch it, it has, in a very small fraction of time, has a tangential velocity, right? As the name implies, tangent to the circle, right? Tangent to the disk. You also can locate the position of that point, right? So there's a certain r from the center of the coordinate system, the center of the disk. You walk over from the center and you locate where that point is, that's your R, okay? And you can figure out the direction of omega, right? Yes, imprecisely it's this, right? We can just say this is omega, right? And be done with it. And you can say it's just counterclockwise, but we want to be a little bit more precise than saying counterclockwise. And the way you figure out the direction is to say velocity, tangential velocity, this velocity here, is equal to omega, the vector, crossed with position, the vector. Okay? So which way does omega point to make all this consistent? And omega points upward like this. That's omega, the vector, right? So this is kind of up here is an imprecise way of saying what omega is, right? Angular velocity, counterclockwise. I mean, if you're just first starting off with this stuff, it's perfectly fine to say it's counterclockwise, right? That's a reasonable thing to say. But now, since you know vectors, we want to be a bit more precise. Now we're going to say this, right? Omega, the vector, points up like this. Okay? So omega cross r is your velocity, right? So again, if you're not sure where omega is, try to point in a certain direction, do omega cross r, see if it's consistent with the velocity, right? Velocity is easier to identify, tangential velocity, right? As you watch something rotate, you can certainly look at it and say, oh yeah, the little point here is going that way or something, right? So omega cross r, try this out for this example here and make sure your thumb, right, in both the right-hand rules, right, well, the two different ways to do the right-hand rule, the fixed finger method and the curly method, both the thumb is the result, right? So make sure your thumb is pointing in the direction of velocity, tangential velocity. Right, so I'm going to write that down just so that it's not confusing. So this is tangential velocity. This is the angular velocity, and that's r is position, right? They're all vectors. How are we doing?
Good. I think a lot of them are just confused about like the curl rotation and like how to use right hand roll with it.
The right hand roll, yeah. So you do want to practice the right hand roll, right? As I said, it's something that's really important. It's going to come up a few different times in this class. It's going to come up in the next class, Physics 2, quite a bit, right? So that operation between two vectors, you definitely do want to practice that. Check out my video that I posted that uses Desmos, right? That's probably a really good way to visualize it. You can also take pens, pencils, right? Make vectors for yourself and practice the right-hand rule using that, right? You need something three-dimensional, right? You can only get so far with a two-dimensional diagram. Because the right-hand rule is three-dimensional naturally, right? So it's really hard to maybe see it when I draw this, right? Because I'm trying to draw something three-dimensional in 2D, right? So the trick with it, point either your forefingers, right? Depending if you're doing that method, or your index finger, point it in the first vector, right? Omega, right? In this case, it's omega. In the previous case, it was theta, right? So the cross product is like multiplication, it's like addition, right? It's like subtraction. These are mathematical operations, right? This is not multiplication, of course, this is a cross product, but it's a mathematical operation, right? So it can be done to many different vectors and lots of different vectors. So in this case, it's theta, that's the first vector. In this one, it's omega, that's the first vector, right? So you want to point either your index finger or your forefingers in that same direction. Then in the forefingers curling way, you take omega, where omega is, right? Omega is pointing like that, and you curl your fingers towards R. So omega cross R, your thumb points that way, that's V, right? In the fixed finger method, the index finger goes along omega, and your middle finger goes along r. So you might have to rotate your hand. So if you kind of do this, right, your index finger is pointing down. So then just kind of rotate your hand, right, like this. And you'll notice that r is kind of coming towards you, towards the screen, right? So then omega is up like this, and r is like this, and then your thumb is pointing in the direction of v. Right? Does that make sense? Do you have other ways to think about the cross product? Jericho, Kyler? What helped you when you, because the cross product, as we know, is kind of confusing when you first see it. What helped you to kind of visualize this?
I feel like just practice.
Practice, but how did you practice so that, tell the class how you practice so they can practice the same way maybe.
I think just your own examples. I think Desmos is good. Also, just drawing your own vectors in your own diagram like this,
Yeah.
and then applying the right-hand rule. Because I think we do have some confusion about the radius vector right now. And
Okay.
I think just because it's a 2D drawing, some people thought it was pointing down, and we had a question, how could it be 180 degrees apart? But
Oh yeah. So like, let me try to draw this maybe. So this is one orientation, but what does this look like from the top-down view, right? If I came up here, what would this look like? Well, it will look like, let's draw the disk. Right, from the top-down view, the disk would look like this. My point along the edge of the disk, right? Let me try to keep the colors the same, so I'm picking the same point. So there's the point, right? So there's that point. So from the center of the circle, r would be like this, right? And then the velocity vector, tangential velocity, would be tangent to the circle, will be like this, right? So note, let me back up here. Maybe that way you can see them side by side, right? So yeah, 3D things, you just draw it in different orientations. That's one way to figure out. I mean, maybe try to draw it from the bottom view or something, right? So draw it in different ways. So here's your vector r, right? So from the center, I'm coming to the point. So from the center, I'm coming to the point. And then velocity vector is pointing like that. Where would the omega be, right, in this orientation? Omega would be coming right at you, like this. Right? And so the way I would draw that is I would draw a circle and I put a dot and I would say that's omega. Right? Does that make sense? Right? So we can do the right-hand rule in this orientation, right? So omega cross r. Omega is upward towards you. So if I start my 4 fingers upward, then what I do is curl towards the direction of r, right? So upward, and r is downward. So I curl, and notice my thumb points that way, right? Which is the direction of the velocity, right? I can do the other method too, the fixed finger method, right? So I start with the index finger being on omega, okay? Index finger along omega, point that way. And my middle finger has to be in the direction of r, so a little hard to orient my hand here, but so it's kind of like that. So my index finger is along omega, my middle finger, right, this one is coming downward towards r, and then my thumb still points to the right, which is the direction of the velocity. Right, so yeah, so it has to be your right hand. You have to practice a lot to get the hang of it. It does take a lot of practice. So go watch that video that I posted. I think that will really help, because the nice thing about Desmos, one, it's free, so everybody can use it. The other thing is you can kind of pick up the coordinate system, right? Which when you draw on paper, you can't really do anything with the coordinate system. I can't just pick it up and rotate it, but in Desmos, you can literally, kind of do this and look in sideways and, rotate it around. So that's one thing. And the other thing is also you can create your own vectors. You can just make up vectors that point in different directions and practice your right-hand rule. And Desmos has a way of doing the cross product for you, right? So if you give it a vector in a certain direction and another vector in another direction and say do the cross product, it'll tell you what the result is. So that way you can practice, right? So I mean, don't always use its because you don't have access to Desmos during an exam. So you want to be able to do the cross product yourself, but it's a good way to practice because you can just say, okay, I have a vector that points in this direction, I have a vector that points in this direction, pause, do the right-hand rule yourself, see if you can predict what the result should be, and then have Desmos show you what the direction is, and that way you can check yourself, right? Have you tried that, doing that? Yeah, so do that. That'll give you a bunch of practice because, like I said, it's three-dimensional, and maybe you don't want to use Desmos. You're sick of computers and you want to be in the real world. If that's the case, grab some pens, put some Play-Doh or something, right? Stick them in together to in an orientation in a way, and then that way you can practice the right-hand rule kind of in real life too, right? Other questions? Okay, we'll do more practice as we go, so you get more of the swing of things. All right, so now that we have the terminology, right? We have the terminology that we need. Let's talk about some kinematic equations. Okay, and it's helpful if you can split your notes into two. That way you can compare what we had before for the translational kinematic equations with the rotational equivalents. Okay. So let me write down the translational ones. Okay, so these are ones that you are familiar with now, right? You've done some problems involving the translational, kind of linear, maybe another word for linear, right? So those kind of linear kinematic equations, imagine dropping something on the ground, imagine tossing a ball, right? That sort of thing. These will work for that, right? Now we want to come up with the rotational equivalents, kinematics of rotation, describing rotation, right? So the nice thing is you don't have to get another whole different set of equations. All you have to do is just copy these and swap out the terms, okay? So position, final, right? So what's the rotational equivalent of position? That's theta f is equal to position initial, theta naught, plus the velocity, right? Average velocity, angular velocity times time, right? So you see the symmetry here, that all you have to do is just copy and then swap out the terms, and you get the rotational equivalents for free, essentially, right? So again here, velocity final, so omega final is equal to omega initial plus the angular equivalent of acceleration is angular acceleration times time, right? And we're done with that equation, and so on, right? So we have all four that we can write down by swapping out the linear variables for the angular variables. Okay, so let's try out a problem so we get an idea how to use these. Okay, so here's an object, let's say it's a ball. And what we are told is we're told a few things about its kind of starting state and ending state. Let's say that's its axis of rotation. We are told that the angular velocity initially is 0 radians per second. The final angular velocity is 10 radians per second. And it does this by going from an angle of 0 radians, and the final angle is 20 radians. We're asked to find the acceleration of this. Okay, so it's going from not spinning to spinning. It does it over a certain position, angular position. What is the acceleration? Right, so that's what we're told to find. Okay, so I'm going to pause here, have you think about this for a second before I go and do it, right? So I'm going to put, let's see if I shift these. Okay, so I have the kinematic equations up here at the top. Which one would you use to find acceleration? Tell the LAs, let's say 1, 2, 3, 4, the number of equations. Would you use 1? Would you use 2? Which one would you use to solve this, right? Going back to a little bit of kinematics, right? It's been a minute since we've done kinematic problems. What are their thoughts?
One answer for 4.
One answer for 4. There's 300 of you, so what is everybody else's ideas?
3 answers for 4.
Okay, getting up to 300. If slowly, slow and steady, but getting up to 300.
About 8 answers for 4.
All right, so getting some consensus around 4, right? So remember with kinematic problems, look at the equations, look at what's given, look at what you're supposed to find, and try to make a best guess of which equation to use, right? So here, looking at 4, popular answer for 4. Why is 4 a good idea? Well, you're told the initial velocity and the final velocity, you're told the initial position and the final position. You're asked to find alpha, the acceleration, and you have one equation, one unknown, everything else is known. Great, right? So that's the one you should use. Can you use this? Yes, right? You can use this, you can use this, you can use all 4, right? Because it's a constant acceleration problem, so the kinematic equations work. The only thing is you'll have to do a bit more work if you use number 3, right? If you use number 3, you still have to find time. You can use this to find time, for instance, right? So you can kind of figure it out combining different equations, but hey, if you can use one equation, why bother using 2 or more, right? So if you can do it with 1, go ahead and do it with 1, right? So the 4th one works. We'll take the final velocity squared is equal to the initial velocity squared plus 2 alpha times theta f minus theta naught, right? So the initial velocity we know is 0. The initial position we know is 0. Get rid of those terms, right? Make sure you solve for alpha first, right? Make sure you get in that good habit of solving for alpha first. Once you have an equation for alpha, then you plug in the numbers, right? And when you do that, you should get alpha is equal to 2.5 radians per second squared, right? So it kind of has meters per second squared, kind of should remind you of what we had for the linear case, right? So the units are similar but not the same. questions about that?
We have a question asking for a visual representation of a position going from 0 to 20 radians. Like, what would that mean on the circle?
Good question. So, what is going around a circle, right? How many radians is going around a circle, roughly? You all can tell me on that discussion. Or Jericho can help you out. So what did you say, 2 pi?
Yeah.
So 2 pi is roughly what? What's the number? What's pi roughly? You all know this, right? I'm not asking you to memorize 18 digits of pi. Well, what's pi roughly? Yeah, 3, roughly 3. So if you say 3 times 2 is 6, right? So roughly 6 radians is going around a circle. So 20, that's several multiples of 6, right? So what, about 3, maybe a little bit more than 3, right? So it's like spinning around like 3 times or so, right? So yeah, just, 20, we don't really use radians kind of in everyday life, right? You don't look at your car tire and say it spun 200 radians or whatever, right? You don't really do that. So it's a kind of a unit that's maybe not as familiar, particularly when you have large numbers of it, because you probably know pi over 4 radians or something, right? Like that's probably showed up in some math example, math problem. But yeah, you can always convert it to something that's like a revolution or degrees even, right? Cool. So let's continue this comparison, right? So we're starting off with kinematics, describing motion. We're comparing the translational linear case to the rotational case. And that works for kinematics, but it also works for other things, including F equals ma, right? So when we wrote down Newton's second law earlier for the linear case, we said very generally what that means is when you sum all the forces on an object, if there is a net force, it will cause momentum to change with time, right? And we said that momentum, more on that in a bit in the class later on, is mass times velocity, right? It's a very important quantity that involves 2 ideas of physics, right? Mass and velocity combined is what momentum is. So Newton's second law says that, okay, if you have an object, it has a net force on it, then its momentum will change with time. If there is no net force on it, then its momentum will not change, right? Thus Newton's first law, an object in motion stays in motion, right? Object at rest stays at rest. Now, we can also look at this in a rotational sense and say, okay, this is the linear case. What about the rotational case? Well, the rotational equivalent of a force is a torque, right? So if we sum up all the torques, it says if there is a net torque, it will cause angular momentum to change with time. Okay? And there's 2 ways to think about angular momentum. One is to think about kind of a case where there's a string, and let's say you're connecting a ball at the end of the string and it's going around counterclockwise, right? So it's maybe traveling that way. And so this ball has a linear momentum, right? It has a p, because there's a mass times the velocity, right? So it has a tangential velocity at that moment. It has a linear momentum. It also has a certain distance away from the rotation point. So one way to define angular momentum is to say r cross p. Okay, that's one definition of angular momentum. It doesn't quite look like this, right? But there's one that actually looks almost exactly like m times v, And that you can define angular momentum to be the moment of inertia times angular velocity. Okay, and compare this to this. Right? Linear motion, rotational motion. Rotational motion is a little bit more complicated. It involves cross products and things like that. But there's a lot similar to it, right? There's more things in similar than you might kind of imagine. This is both momentum. One's linear, one's angular. This is mass. You're pretty familiar with mass, right? How much stuff does something have? The more, if it's made out of more things, more stuff, more atoms, it has more mass. This I is the moment of inertia. It's the equivalent of mass for rotation. If something has more moment of inertia, it's more difficult to get it to rotate. And it's also very difficult to get it to stop rotating, right? For instance, the Earth has a very large moment of inertia. That means like if you just want to stop the Earth from rotating, it's going to take a lot of considerable effort, right, to stop it from rotating. Then the velocity is velocity, just this is linear velocity, this is angular velocity, right? So notice the similarities with how it's defined, right? Keep in mind there's an alternative, right, for angular momentum where you can kind of do it by particle. The connection here, these are actually pretty similar actually, even though it looks different, is that this you get by doing a sum over all the particles, right? So if you have an object like a disk, if you consider every single particle having a linear momentum and you add them like this over and over and over again, you will get this, right? And if you want to see the details, I think it's in the textbook of how to relate this. Certainly in the OpenStax textbook, they will walk through the steps of getting from here to here. But just keep in mind there's kind of an individual particle level of angular momentum you can think about, but also collectively, right? Like as an object has certain angular momentum. So I'm going to talk a little bit more about what I is. This is the moment of inertia. Okay, so this up here and this up here, they're the more general Newton's second law for linear motion, rotational motion, right? But recall that we took this and we said if mass is constant, if m is equal to a constant, then we get the familiar sum of the forces is equal to mass times acceleration, right? We get F equals ma. This is the general one, right? This is what the big idea is. The simplified version of that, right, for a specific case of mass being constant is F equals ma, right? This is not the general one, right? Now, looking at the rotational one, that's the general one. You might say, okay, what's kind of the F equals ma equivalent, assuming that the moment of inertia doesn't change, right? In the case of rotation, it's not the mass that matters, but the moment of inertia. And we can play the same game as we did before. We can take this, right? And we say, okay, what is that? Well, the sum of the torques has to equal the derivative of this thing called angular momentum. We can rewrite angular momentum as I times omega using its definition. If we assume I is constant, we can pull it out of the derivative where you have I times the derivative with respect to time of omega. And this, right, a derivative of velocity is an acceleration, right? So you're left with I alpha. Okay, so this is the linear case simplified to a constant mass, right? So Newton's second law simplifies to F equals ma. Newton's second law for rotation simplifies to the sum of the torques is equal to the moment of inertia times angular acceleration. right? So you will do problems equivalent to what you do with F equals ma, and assuming that the moment of inertia doesn't change, this is what you're going to use, right? And look at how similar they are, right? They're very, very similar. The force equivalent is torque, the mass equivalent is moment of inertia, the linear acceleration is angular acceleration, right? So they're very, very similar. Okay, questions, but we're going to spend some time talking about the moment of inertia because that's a new idea. But how are we doing in terms of this, right? So seeing the comparison of the two different Newton's laws, linear case versus the rotational case. Doing okay?
Yeah.
Give you a second if you have a question. It takes a minute to type in, so give you a moment to type in your question. Okay, so keep asking questions. We'll keep an eye on it. We're going to try to understand what the moment of inertia is. And to do that, let's start with a demo and see how it behaves in real life. And then we'll try to describe it more mathematically, right? So let's look at this video and then we'll come back. So in this demo, we're going to look at moments of inertia. So here's a disk, and this is a hoop. They have different moments of inertia. So the moment of inertia of a disk is 1/2 mr squared. Of a hoop, it's mr squared. There's no half in front. So you can see they're about the same size. Their radii are the same. They're about the same mass. So what we're going to do is try to roll them down this incline and see what happens. Which one of these gets down first? So let's try to start them off approximately at the same place and let go. So you might want to take a second to think about which of these do you think is going to come down the ramp first. So let's try this out. So you can see that this disk came down first, and it has to do with its moment of inertia. So this has a smaller moment of inertia than this hoop. So what that means is that as these are rolling down, the one that has a larger moment of inertia has a larger resistance to rotate. That's what it means to have a larger moment of inertia. This one has a smaller moment of inertia, so it has an easier time to roll and come down the ramp before the other one does. So again, the radius, about the same for each one, the mass is about the same, but it's a matter of how that mass is distributed that matters. In this case, you can see that all of its mass essentially is concentrated at its edges, where in this case, it's more distributed. So as it rotates about this point, it has less mass that's too far away from its rotational axis, as opposed to this one, where all of its mass is far away from its rotational axis. So this one has a larger moment of inertia. It finds it harder to roll down the ramp, and that's why this disk comes down first. So this is a demo of different moments of inertia. All right, so let's take a look how you would describe this more mathematically, right? So the moment of inertia, where we're going to start off is thinking about for discrete particles. Okay, now it's a simplification just to get an idea. We did something similar with the center of mass, right? If we consider an object made out of a bunch of points, then we can just count the points, right? But when you're talking about a real object like a pen, clearly this is not made out of a bunch of points, right? So it's an extended object. But if we understand what to do with particles, we can extend it to kind of more real objects that are not particles, right? So I'm going to start off with bunch of beads. Imagine you had a bunch of beads that you're connecting with a very, very, very light string or some sort of metal, right? That is very, very small, that we can ignore it. And we're focused on just the particles themselves, right? So let's connect them together so they can rotate as one object, okay? And put center, let's say this is the center, right? The way I can calculate the moment of inertia, right? It's how, as we saw in the demo, it's how distributed the mass is. More concentrated, right? The moment of inertia is smaller. If you have mass that's distributed really, really far away from the center of rotation, then you have a larger moment of inertia, right? It's not just mass here, right? It's how the mass is distributed. So the way you can define the moment of inertia, I, is that you do a sum over all the particles that you have, however many, 10, 20, 200. What you're going to do is take each mass of each particle, find its position, the magnitude of its position, really, because you're going to square it. Unlike the case of the center of mass, the position, the negative or positive of it doesn't really matter. All you have to do is figure out how far it is from the axis of rotation, or the axis you're interested in finding the moment of inertia of, and you take the square of that distance, right? So let's take this particle, for instance, here, right? So this one right here has a certain m, call that mj, right? J is just the index, 1, 2, 3, 4, right? You can count the particles. So this particular particle has a certain mass. It has a certain distance, right? Rj from the axis you're interested in finding the moment of inertia. Right? And all you have to do for the moment of inertia is just go one particle at a time, multiply its mass by the square of the position, and do that over and over and over again, right? Just keep adding them up, and when you add everything up, that's your moment of inertia. One thing to notice is that the moment of inertia depends on the axis you're interested in. So when I have my pen here, unlike mass, my pen has a certain mass. We can all measure it and agree on what the mass is. Its moment of inertia is not a predefined thing that you can just say, oh yeah, the moment of inertia of the pen is this. Okay? You have to define the axis you're interested in, trying to rotate this pen. If you say, I want to rotate the pen about this point where my fingers are, then it has a certain moment of inertia about that point, right? Because you come from the place you're trying to rotate the pen and find all the distances to all the particles and then add them together. I can also shift my fingers and say, okay, I want to rotate my pen around this point. And then the pen itself will have a different moment of inertia, right? So the moment of inertia isn't something like mass that's kind of inherent to the property of the object. It really depends, it is dependent on mass, but it also depends on the axis you're trying to rotate about, right? So if you're trying to rotate the pen about this axis, right, you're trying to kind of do something like this, where you're trying to rotate about that point, or you're trying to rotate about this point, or you're trying to rotate the pen kind of this way, right, along the long axis. You can still rotate the pen that way. All of those will have different moments of inertia, right? So when you're trying to find the moment of inertia, you have to stop and think about what's the axis you're interested in doing this about. Okay, so that's for discrete particles. It should kind of remind you of the center of mass. It's similar to center of mass, not the same calculation, but kind of has similarities between the center of mass. Now, you might say, okay, what if I want to do this for a real object, right, that isn't a bunch of particles? What do I do then? Well, maybe your real object kind of looks something like that, right? So I'm just drawing some random shape, right? It's a physical three-dimensional object. You're not going to be able to count the little particles because it's a physical, real thing. So you can still go and do this. You can still follow this process. Maybe you want to find the rotation, the moment of inertia about this axis. right? I'm drawing the dotted to go through the three-dimensional object, and you're trying to find, okay, what would happen if I try to rotate this object about this axis? Okay, can you do this? For extended objects, you do something similar, except you do an integral, right? You do the same thing, but you have a r squared, but you, instead of taking the masses of single points, you're taking a little dm, right? Which is a little bit of this. So what is a dm? You come to this object, you break off a little chunk of it, right? That little chunk of this three-dimensional object, that's your dm. And then you find, okay, well, how far is it from the axis of rotation? Okay, it's some r away. You take r times dm, and then you add. Integral is a fancy way to add, right? Notice the big S here. It's the long S, right? S for sum, right? So integrals are a way to add things. So you add that to all the other particles, right? So you have a little chunk over here of dm. That's another dm. How far is it? It's this far away. R, you add that. You add that. You keep adding every single part of this, right? That's what an integral is. It's similar to this, except this you can kind of visually see you're counting 1, 2, 3 particles. A dm is an extremely, extremely small part of the object, not something you can pick up and count, okay? So I'm going to show you a quick example of how you would apply this to a real object. That way you are aware of the kind of the process of going about doing this. You don't have to do this yourself. Often, if you have an object, you can use a table to figure out what the moment of inertia is about a certain axis. But it's important to be able to be aware of how you would go about it if you needed to do it for a new object, right? Nothing that you've seen before, and you can do that. So let's start with a simple shape. I'm going to start with a hoop or a ring. Okay, so let's say we have this hoop. And some thickness to it. And I want to find the moment of inertia through kind of this long axis right here, right? I want to know what the moment of inertia is through here. How do I do this? It's not a bunch of particles, it's an extended object. So what I have to do is use the integral form, the integral of r squared dm. How do I do it? I need to break it up into small dm's, and that's my choice, how I break it up. The only thing is dm's have to be really, really small. Your dm can't be the whole hoop, right? That's all of the mass. You can't do that. You have to break it up into small parts. And how specifically you do that, that depends on the problem, depends on the shape of the object that you have. For this particular object, because it's a hoop, I'm going to cut little slivers of it off. That little sliver of it is my dm. Okay, so from the axis of rotation in here, right, if I can draw from the inside out, from the axis of rotation there's a certain r, right, that's the radius of the hoop actually, right, because every single dm that I draw will have the same distance, right, because if I take this chunk versus this chunk, each dm is r distance away from the axis of rotation, right? Because that's the radius of the hoop. So if I went over here and cut off this part of the hoop, right, and that was my dm, the r would still be the same. Okay, I have to do that. You have to break up the hoop and you have to actually add up all the dm's, and so this is just one dm, and you just have to go around the hoop and add up all the little dm's, right? So when you do this, you realize, okay, if I add up all the dm's, every time I try to do that, the r is just big R, the radius of the hoop, right? So that r is just the same for all the dm's. That means it's a constant. That means I can pull it out of the integral. So what I'm left with is an integral of r squared integral of dm. Okay, and integral of dm, integrals are a fancy way to add, right? So don't get too scared by integrals. They're just ways to add things up, right? It's something that's sometimes not emphasized in calculus, is that it is a way to add, right? It's a fancy way to add. So when you see something like this, what is it saying? Add all the dm's, right? So if I go all around the hoop and add up all the dm's, what do I have? Well, if I add up all the dm's, I'll just have big M, whatever the mass of this hoop is, right? If I add up all the little masses, I have the total mass, right? So that's why I mentioned in the demo video that the moment of inertia of a ring or a hoop is equal to mr squared. Right? So when you look at a table, right, now since you know what this is, you don't have to do it every single time. You can go ahead and look at a table. You'll have these equations on your equation sheet for an exam, right? You don't have to do them every single time, but it's good to be able to say, if somebody asks you, where the heck did mr squared come from? You have some argument that you can make. Okay, well, actually, let's go back to the definition of what a moment of inertia is. We do an integral, and therefore, that's how you get to this, right? And you can do the same thing for a disk, right? So if you're interested, you can go ahead and do the integral. You'll get a 1/2, right? There's a 1/2 mr squared. You'll see where that comes from. You can do that with a disk. You can do that with a shell, a sphere. And then if you look at the textbook, there's all sorts of shapes, right? Cylinders and all sorts of shapes that you can have. And what's nice is that once you know the basic shapes, you know what a prism's moment of inertia is, right? When you know a few shapes, you can add them together to make more complex shapes, right? So if you want to know the moment of inertia of a car, for instance, you can just make it out of a bunch of rectangular prisms. Right? If you want to know what the moment of inertia of the human body is, well, look at the arm. It looks like a long cylinder, right? Look at your torso. It looks like a cylinder, right? So you can put all these cylinders together and kind of roughly get a rough idea of what the moment of inertia of a person would be, right? How, if you start spinning, what's your moment of inertia? You can start building that using simple shapes, right? So that's why it's important to understand where the simple shapes come from, doing these integrals. But yeah, so that you have an appreciation for where these equations come from, because you'll see a bunch of these in your textbook, in the equation sheet. So yeah, you'll see some with certain factors, 3/5 and things like that. It's good to kind of think about, okay, oh yeah, it comes from doing an integral, right? Okay, questions about that?
There's some confusion about, I guess, just the variables again. If you could re-explain the R and the DM.
In the hoop example?
Yeah.
Yeah, sure. So go into the notes. Starting with our definition of what a moment of inertia is, R is the distance to your DM, right? So you're taking a mass, right? So let's say you're taking something like a water bottle, right? Something physical object, and you're breaking it up into small bits and pieces. Each piece has a certain distance from the axis of rotation, right? They're not all the same, generally speaking, right? So the R here is how far is that particular DM from the axis of rotation. Once you know that, you go to the next one, a different R, and you add all the DMs together, right? In the case of the hoop, right, where that's what we're doing, we're taking the hoop or the ring, right? If you have a ring, you can kind of imagine, take it and you can kind of look at it, right? If you take a hoop or a ring, then it's got a mass as a whole, but to do the moment of inertia calculation, we're trying to cut out little bits of DM, little bits of pieces of the mass. So we take that little sliver of it off. Imagine like taking a sharp knife and cutting it or something, right? So cut it, and you get a little piece of it. then the r here is how far is that little piece from the axis of rotation, right? The little r. But because the hoop is a circle, right, it's r for all the little pieces of it, right? Every single dm is the same r. It's the radius of the hoop or the ring, right? That is the same. So I'm just saying, okay, that goes in here, right? The big R is the radius of the hoop. I can substitute for the little r, and that way you have the radius, it's a constant, you pull it out of the integral, right? dm's are a little chunk, right? Just think about a very, very, very small amount of the mass, right? And so that's what's left in the integral. You have an integral of all the little dm's. And integrals are a fancy way to add, so you're saying add up all the dm's. Well, when you add up all the dm's, you have mass, right? The mass of the hoop, whatever it is, right, is what's left over. Does that help, maybe? Other questions? Okay, so let's do an Insta poll here. Switch over to the computer and send you an Insta poll your way on the concept of moment of inertia. Zoom in here, maybe a little bit more. Okay, so you have three objects here. You're asked to compare the moments of inertia. So let's take a minute and a half, look at this, ask questions about this as we go, and we'll be back in a bit. Okay, let's look at the question here. Three objects, right? There are equal masses, different shapes. You have a solid disk, you have a ring, you have a square that's hollow. So we're asked to compare the three moments of inertia, right? If they're rotated about their centers, right? The axis is kind of coming out of the page. If you rotate them about the center, what is the moment of inertia like, right? So a good thing to start is the disk and the ring, right? Because they are both the same mass. How the mass is distributed is different. So disk or ring has the larger moment of inertia, and then we can figure out what the square is, right? So I think we're still waiting on some of you to answer. Make sure you're putting your answer in as we go. Let's take a look at kind of how this is spread out. We have square being the largest, then you have ring and disk. right? So ring over the disk, right? The ring's moment of inertia should be larger, right? It both have the same mass, but the ring has more mass away from the center, right? If you shove more mass away from the center, then the moment of inertia will be larger, right? So the ring over the disk should be the smallest, right? Then when you consider the ring and the square, again, they have both the same mass. So how do you tell the ring over the square, right? So one thing to, again, to focus on is that how far is the stuff, right, from the center. If you look at the ring, right, every single little piece of the ring is r distance away, right? There's no other option. It's a circle, right? But if you look at the square, some of it is r distance away, right? This is 2r. But if you go from the center to the edge here, that's the distance of r. If you go from the center to the top, that's a distance of r, right? So there's certain parts of the square that have the mass distributed just like the ring does. But the square also has these edges, right? So from the center to this edge is not r, is larger than r, right? By a square root of 2, right? You can do the Pythagorean theorem there, right? So from the center to the edge is a little bit further than any part of the ring can get. So the square has a little bit more mass spread a little bit further than the ring does, right? So then square is larger, right, in terms of moment inertia than the ring is, right? So does that make sense, right? Are there questions about this particular Instapol? No. Right. So hopefully that's clear, right? So you get a kind of more intuitive understanding with something like this and like a conceptual question like this, but you also have the mathematical way of defining the moment of inertia now, right? So you have both. Okay, let's go to a problem and kind of put all of this together in a Newton's laws problem. Going to the notes here. A Newton's laws problem that involves both linear motion and rotational motion, right? So since you now know both, you can do even more complex problems, right? So what we're going to set up here is a disk that can rotate about the center, that is connected to a mass through this wire. Okay, so here's a mass m. The disk itself has a certain mass. It has a certain radius. Okay, so we're going to ignore friction for a second. So right through that middle, you might say there's some friction there, right? We're going to ignore that because we're going to say it's very minor. Let's say it's a bearing that's well kind of engineered to be low friction, right? So you set up this disk and you hang this mass, and you can see if you let go of this mass what's going to happen, right? If you hold on to it, it'll stay put, but the minute you let go of the mass, you know what's going to happen, right? What is going to happen? This disk is going to start spinning, the mass is going to start falling. So what we're asked to do is to find a few things. We want to find the angular acceleration of the disk, the acceleration, the linear acceleration of the box, the mass that's hanging out. And we want to know the tension of this cord right here. Right? There's a cord that's hanging off. What's the tension there? Several things to find. So when you start a problem like this, right, don't forget there's a recipe to follow almost, right? So there's a system to follow. Stick to that, right? And it won't draw you in a bad direction if you stick to the system. Don't skip the process of solving the problem, right? What is the process of solving the problem? Draw a free body diagram, at least one, right? In this case, two, right? There are two objects. So what do we want to draw a free body diagram of? Well, we want to draw a free body diagram of the box, and we want to draw the free body diagram of the disk. Okay, so I'm going to pause so that you can take a second to do this yourself, right? Good practice. Look at this, right? And draw yourself free body diagrams of the box, of the disk. Think about the coordinate system. Which way is X? Which way is Y? Those things are going to matter, right? Because we can see what's coming up next is applying Newton's second law. When we're applying Newton's second law, we need to know what's positive and what's negative, right? So therefore, think about the coordinate system as you go as well. Brownie points are posting on that discussion, so Kyla and Jericho can give you thumbs up for your work. It's important because that way we kind of see what you're thinking too. If we're missing something, we can see that. If there is points of confusion, we can see that. So post your results. Okay, so hopefully you've had a chance to put some forces down, right? Remember, free body diagram, only forces, only external to that object, right? No torques, no accelerations, none of that goes in a free body diagram, right? There could be torques, right? But we'll solve for that. But you should put down the forces, the external forces, right? Well, on the box, what do we have? Well, we have a tension pulling up. We have its weight, right? M times G is its weight pulling down, right? Those are the two forces acting on the box. On the disk, what do we have? Well, we have a tension pulling down, right? Remember, it's the same tension, the magnitude is the same, but it's from whose perspective, right? From the perspective of the mass, the tension is trying to pull it up. From the perspective of the disk, the tension's trying to pull it downward like this, right? So the direction of tension will be different because it depends on the perspective, right? You're drawing a free body diagram from the perspective of that object only, right? Okay, so then the disk itself has a mass, right? Goes through its center, right? Center of mass, big M times G, its own weight. And there has to be one more force here, right? Because you can look at it and say, oh wait, if it's only this, the disk is going to start falling downward, right? The way it's set up is there's a hinge point that it's rotating. The disk is rotating, but it's not falling down, right? Because it's being held up by that point. So at that point, there is a normal force pointing upward, right? There has to be a force there. Otherwise, the whole thing will start accelerating down to the ground, right? So if it's being held up, it's being held up by the normal force as a result of the bearing or something, right? So whatever there's the bearing that's holding it up, or a screw or whatever it is, it's holding it up there, right? Okay, so well, we're coming up on the end of the class here at 10:30, so we're going to pause here, right? We'll continue this problem, but if you have the time, you can continue thinking about what the next steps are. The next steps are to apply Newton's second law, which we'll do next time. Before we go, any questions about what we've talked about? Everything's doing okay? Can we switch to the computer real quick just to look at the schedule here, right? So we're on June 23. The Monday, we have a full week of class this week. Next week, we're going to have midterm 2 on July 1st, right? That's the Tuesday. Friday is going to be a holiday, right? 4th of July, the holiday. So it's going to be a little bit of a short week there. You have access to the 2 homeworks that will be covered in midterm 2, right? So one due soon, right? And then there's another one due on Friday. So there are 2 that are due, and so that's the material that's going to be on midterm 2. It's not comprehensive. It's focused on everything after midterm 1. I'll send you more information about that soon. However, notice that in physics, these concepts add together, right? So you do need to know the concept of velocity, even though that was the early stuff. So, but the focus will be on the new material, right? So certain definitions, there's no getting around. We still need those definitions. Somebody asked about practice exam. Yep, there will be a practice exam. So everything like we followed for midterm 1 is the same. So same for midterm 2. More information about that soon. Ask us questions on that discussion. Make sure you're coming to drop-in hours, talking to us about anything that you find confusing. We're happy to help. So with that, we'll see you tomorrow.